Welcome to tutorial 4 of agent-based modeling for psychologists. So today we're going to be picking up where we left off in tutorial 3, and specifically we're going to work a little bit more in the interface. We're going to introduce plots so we can measure things. We're going to implement some functions in our code to just make things work without error, to kind of catch things preemptively. But most importantly, we're going to build in an evolutionary algorithm. We're going to build in a sense of reproduction so that we can really harness the strengths of agent-based modeling in looking for emergent properties. So unlike other kinds of modeling where there's a solution we're attempting to define a set of parameters to find, rather we just kind of set the parameters up from first principles and see if they produce the phenomena in question. So it's this emergence that's really most valuable in agent-based modeling. And I'm going to show you by way of an evolutionary type algorithm where agents are reproducing and blind variance is being introduced into the model to see if that improves the outcomes for the agents. We're going to build that in. Now, that's not something that's necessarily going to show up a lot in social psychology or cognitive psychology, but it is something that shows up in my field of cultural evolution and thinking about the way ideas and beliefs and technologies and artifacts transmit over multiple generations. So here we are in our model, and there's a few things we're just going to introduce. First of all, we're going to play with our align function. Now, this is primarily for aesthetics. We can select things, we can shape them and change their sizes, but when we use align, we can for example, stretch them right, so they all start to align to the left or right, and they all have the same sizes. So one can go ahead and do this just to kind of make everything nice and straightforward. Let's even distribute them vertically so they're all same distances. Now, what we probably want to do is move a few things to the other side. So this is going to be up to you, but variables that tend to be actually mine, I normally make this bigger, don't I? Variables that are relevant to the model, I tend to put on the left. So parameters that we're going to change as a function of our actual interest. Generally, I put these things, I said the left, didn't I? Put them on the right. And just merely functional things tend to put on the left. This is just a way to stop being confused and to keep things sensible. There might be some developments in the near future in Netlogo where there's a way to hide certain tabs, certain widgets, which if anyone from Netlogo is listening, that would be greatly appreciated. But for the moment, we need to implement our own manual strategy. Now, the model as we have it is a model where these agents, these peeps, run around avoiding rocks and trying to collect food. Agents quickly go extinct. The population collapses. There is a capacity for them to die, but you can see these ticks keep going. Now, we don't want our model to run forever. So in terms of preemptively catching things like this, we want to go to our go command here, and we want to identify some way to stop the model running when, for example, the population collapses. But we might also just want it to stop running after 50 ticks. There's a lot of reasons to want to be able to stop the model. So let's check in with our dictionary and let's look around for where that might be. Probably control logic. Do we see anything here? Yeah, we see things like startup, and we see a thing called stop. We even see things called wait, which we'll probably use later, but we see stop. Stop. This agent exits immediately from the enclosing procedure, ask or ask-like construct. Only the enclosing procedure or construct stops. So if not any turtles equals true, stop. This is what we want. So we probably could just use this line of code. Oh, it's not working. And that's because we have specified turtles and there remains peeps and rocks. So if not any peeps, if the population of peeps collapses, there we go. 899 ticks and it stops. 1399 ticks and it stops. Other ways to do this, if count peeps equals 0, you can stop. and various other things. Or you could even do something like if ticks equals 100, stop. So if you only want the model to run for a little while, 100, it's going to stop. So this is a really useful function just to stop the thing running forever. But we ultimately don't want our population to collapse at all. We want it to keep going indefinitely. So we need to build in a capacity for reproduction. There are many different ways you could implement reproduction in a model like this, and I will probably do an entire video on the different methods and when those methods might be useful. So if we think just about the real world, just about biology, we have sexual recombination. Essentially, you have two agents, a male and a female agent, and in some ways they have some kind of genotype, and then the offspring inherits with 50% probability this allele, that allele, this gene, that gene, whatever. Now that's can be really useful, but you need to make a lot of decisions about what's male, what's female. You need to make decisions about how do we express the genotype. How do these two reproducing agents assort and find each other? What happens to them once they sort and reproduce? What's the energy cost of reproduction? All of this kind of stuff. There are reasons to engage in that kind of strategy. There are less complicated procedures. You could just sort half of the population, the 50% of the population with the weakest fitness score or whatever it is that we're deciding is the target of reproduction, which in our case would probably be their energy level. Are they collecting sufficient amounts of energy? You could just kill the 50% of the weakest and have the top 50% reproduce. Okay. Today we're going to go in something really simple. We're just going to make it so that every time an agent dies, so every time an agent expires, is naturally selected against for some reason, one other agent who is still alive is just going to reproduce. That way, the benefit of this is that there's always going to be 30 agents, or whatever number we set here, there's always going to be exactly 100 agents. If there's 100 agents, one dies, a new one immediately is reproduced by one of the existing agents to fill in that spot. So in this way, our population remains constant. In this way, our food ratio remains constant, and all other parameters kind of remain the same, except we're just observing the selection pressure. We're just observing the effect of selection pressure when agents who we presume on average to be weaker than those who survive die. So what we're going to do is we're going to begin, and I actually don't know what the outcome is going to be here because I've built this slightly different from normal. When we look at our pen down, we can see that agents tend to avoid these rocks. And over time, food just randomly shows up elsewhere. Food is going to show up closer to the rocks, it's just not going to get eaten because the agents never get close enough. So we're going to let the range of vision evolve. So obviously with smaller vision, they can get closer to the rocks. With larger vision, further away. So we're going to let their visual range evolve. Now we might also have to build in like a fearfulness factor that might allow them to overcome their fear, their avoidance of the rocks. But we'll start simple and we'll build it up. We'll build it up from there. So what we have here is our vision variable. This is a global. We set it to whatever it is in the interface. Currently it's 5. Now, when we create our peeps, we don't create a vision variable. And indeed, we don't even have a vision variable for the peeps. Rather, what happens in the go command is we only use vision when they're detecting rocks and they're detecting food. This is happening at a global level. Every agent has the same vision, no matter their circumstances. Now, we might not want that. In fact, we don't want that because we want each agent to have their own idiosyncratic vision value that we're going to allow to evolve over time. I think we can probably keep this as vision. We're going to need to let our peeps own a variable called vision. Okay, a variable for how far each agent can see. Now, if you remember from previous tutorials, if I hit check, we can't double declare our variables. Okay, I like vision. We probably could call this like my vision. Okay, and that would work just fine. Or we could go into our interface and change this title to be initial vision. And very simply, when we start here in our make the peeps, just as we can set its size, just as we can set its energy, we set the vision to be set vision initial vision. Okay, we check it, it works. So we know now that peeps have the variable called vision. Vision is set at initialization based on the value in the interface. And down here, when vision is called, it's now calling the agent-specific value instead of the global value. We'll check it and run it. It's going to look just as it would if it was a global value. And we can make it bigger. And it's going to behave exactly as we expect. So great. We've got vision working at an agent level. But now we need to introduce reproduction and subsequently variation, evolvability, potential adaptation on the agent's idiosyncratic vision variable. So let's go down to their death. Like I said before, there are a million ways to introduce an evolutionary algorithm to something like this. But the way we're going to do it is when an agent dies, when it runs out of energy, when its energy hits 0 or less, they will simply ask one other existing agent to reproduce. So let's do that. Ask, and we know how to do ask and all of that, but now we're going to use our ask one of function, ask one of peeps, and we're going to create a new procedure called reproduce. First, it's correctly identifying that we don't have a function called reproduce. So let's build that, and now we won't get that error. But there is a secret issue that happens here. Ask one of peeps. Eventually, just by chance, it's possible that the agent that this is being called upon, the agent that detects that they have no energy left, will call one of peeps. But that agent set can potentially include themselves. And we don't want them to call upon themselves. It's not going to introduce an error, but what will happen is that an agent without any energy will reproduce, create another agent that might have the same amount of energy, 0, and then they'll immediately die. So we have to account for that. But if we don't want to accidentally call the calling agent, we can put in this nice function of ask one of other peeps. So if we have an agent set with 10 agents and we randomly ask one of them to call some of the other peeps, if we don't have the word other there, all 10 agents in that agent set might be called. But if we add other, it's going to be the 9 other agents. Now let's throw a print down here just to kind of also demonstrate something important about scheduling. Print, I've been called to reproduce. So when this happens, we should see this pop up in our command center. There we are. Keeps happening. Bang, bang, bang. And now we have an error. Let's return to that in a minute. But as you can see, the procedure is being called. Now, if we move this procedure to after the die function, we observe that it's not being called at all. Okay, that procedure is not occurring. So the scheduling around death is really important. Here, if the energy equals 0, they die, then being dead, they can't do anything, and so no further procedures can be called. So if we ever have to kill our agents for whatever reason, but we need them to do something for us, we need them to do it before they die. Now let's find that error and identify what it was. So we're getting the reproduction again. Ask expected input to be an agent or agent set, but got nobody. So this is saying that there are no agents out there, no peeps to call. We've frozen at 2099. If we count peeps, there's one left. Essentially, the population has collapsed, and there's one left, and it's reporting the error because we have the other in there. So the population is essentially collapsing. They can't call in any other agents to reproduce. Let's use a slightly more sophisticated print function as well. So print just reports something like this, but let's say I want to know which agent has been called. And we know that agents have variables like who, and we might want them to kind of like say who they are, right? But once we put anything in these quotation marks, it simply just becomes text. It's a string. Rather than looking this up, I'll just tell you what the solution is. We put parentheses here, we open up parentheses and we close them, and we put word, and we can now string multiple pieces of information. The peep with ID equals. Now we'll close that, and we can type in other variables now. Okay, so we can put in there who variable. The peep with ID have been called upon to reproduce. Okay, close parentheses. And now we can see this is showing up. The peep with ID 61, the peep with ID 25, for example. And we can do that up here as well. And we do it before they die. The peep with ID who, am dead. So now we should get, because of the scheduling, these two things should be coupled. Let's clean this up. Let's start again. It should appear at the top for us. And we can see that I am the peep with ID 48, am dead, and I am the peep with 22 have been called upon to reproduce. And we can see this partnering. 87 dies or is about to die, calls upon 24 to reproduce. So we can get a bit more information when we use print parentheses word in our interface. And if we're debugging stuff, this can be really useful. But let's get rid of that. We don't need that right now. Or we can implement it later if we change our mind. But now we know for a fact that our code is working, and it's asking one of the other agents to reproduce. So for the first time, we're creating agents in our system and not creating them in the startup. So here we use create peeps. Now we might be tempted to think that we can just repeat create peeps, or we could even call upon this to make the peeps. We could call make the peeps and do this again, but it would produce this many new agents, and they wouldn't be inheriting values. So let's have a look at our dictionary. Let's begin by looking at the term that we're initially using. So we've got create turtles or create breeds. But let's swing down to the bottom here to see also. So create creates turtles or breeds out of nothing. But if we go down to say hatch, we can see here, this little icon is that it's a turtle variable. Hatch is something we can ask turtles to do. And if we look at sprout, we can see it's something that patches do. So patches, which we'll discuss in a future tutorial, are kind of the earth, the world, the fundament of the world. They're like the earth. When things come from them, they sprout, okay, to push the metaphor. But when turtles reproduce, they hatch. Turtles lay eggs, they hatch. But essentially what we need to remember is we create when we're calling it from our code without any existing turtles or patches. We use hatch when we want turtles to produce other turtles. We use sprout when we want patches to create turtles. So down in reproduce, we just want to say hatch 1. We haven't put our commands in yet, but if we do this, we know that when we hit 0, the simulation should stop. We let this run for longer than we might otherwise. Let's type count peeps 100. Count peeps 100. Count peeps 100. Count peeps 100. In fact, let's further demonstrate this by getting them to just say print I dead. So we know that we don't want anyone to die there. we want to say print, I made a baby, just so we know that this is being called. And we can see that it is, in fact, being called. Now, without I don't need to demonstrate this, I don't think. I can just state it as a fact. When one turtle creates an offspring through the hatch function, they inherit all of the variables of their parent. They inherit the color. They inherit the position, so the x and y coordinates. They inherit the energy level. They inherit the vision, and so on. Okay. So what we want to do is we want to check the variables that our agents have. We have specified they have 2, energy and vision. So let's go down and create some things. So we can say set energy, and we can just set energy to 100. We're setting energy to 100 because that's the amount of energy that our peeps initialized with at the beginning. And let's set their vision. We can set their vision to, well, this is the thing we're interested in seeing evolve, right? So they inherit vision as is. Now we can't make the assumption in advance that seeing further is better than seeing nearer or whatever. We can make some educated guesses, but here we want to change it. So just as we would change other variables where we've used some basic mathematical manipulation, we can do the same thing down here. So we can set vision plus, we might use random normal with our mean and our standard deviation. So a lot of these changes are going to be very small. Half the time they'll be positive and half the time they'll be negative with a mean of 0. We could do it that way, but we've already used our random normal, and maybe we want a little bit more of a structured change. So let's use a new kind of probability. Let's explore for the first time a thing called a list. So back to the dictionary, let's look at a list. And let's have a look at list. And, well, this isn't super clear, but lists always exist within square brackets. Okay, so they've created a list here that has 2 random values, 4 and 9. They've created a list with the contents of 5. We're going to create a list, which is 0.1 and negative 0.1. So we have a list with 2 items in it, 0.1 and negative 0.1. But we can't do, this will throw an error up because it can't add a list, or at least not with this set of commands, it can't add a list to this variable. So we'll just use the command we're familiar with already, one of, and now each agent, when they hatch out a baby, they will have their energy set to 100, and their vision will be modified by +1 or plus 0.1 or minus 0.1. So if we set this up, we'll hit go. And now we might start to see over time, the agents get closer and closer to the rocks. But when it comes to things like this, it can be really challenging to actually observe their effect. What we probably want to do is look closely at the agents individually, or better yet, look at the agents in aggregate. But actually, before we get onto that, we notice something interesting. It's all brown. Now we know that the trails of the turtles, the pen of the turtles, is based on the color of the turtle. And if we run this eventually, we'll start to see in all runs a degree of homogeneity. We're starting to see blue dominate in the center, pink and blue. I think the blues might win in this one. And the reason for this is because agents inherit the properties of their parents. Now, over time, it's just chance that pink and blue were kind of more successful. They produced more successful offspring. And so we're now fully dominated by the pink and the blue phenotype, which is pretty cool, which is a nice visual way of just being able to check what's happening. Let's have a look here and see if we can see it without the trails. And we can kind of more clearly see the problem that the food is kind of getting stuck around the rocks and the agents aren't quite able to get in close enough. Summer All right, it's been a good long while, so let's stop go. Let's have a look at one of our agents. Its vision is 9.6. The initial vision we set was 10, so it has gotten smaller. Let's have a look at another one. 9.8, it's gotten smaller. So there seems to be some downward selection pressure, but we've just looked at 2. How else might we examine this? Well, we can add one kind of widget, which would be a monitor. Let's put a monitor down the bottom here, and it's just going to ask us for some code. And what we want, we've seen this before in previous tutorials in maths, we want something like the mean. The mean of a list. Show mean x-score of all turtles. What we want is the mean vision of all turtles. So, pretty straightforwardly, we can just write mean vision of peeps. Now this is going to report to 17 decimal places. We don't need 17 decimal places. Let's just make that 3, just for the sake. And now the other thing worth noting here is just like our other widgets, we can have a display name. Let's just change that to mean vision. And now if we hit setup, it should be 10 because that's what it's initializing as. And now let us run. We can see that number, shuffling around. Okay, it's gotten higher. Fascinating. Why aren't they evolving the capacity to get closer? Now, there's some interesting reasons why, and we'll kind of unpack that as we go. But what we can see is that it is working. Now, maybe we want to be able to see this in a more systematic kind of way. So I'm going to zoom out, and we're going to use a new widget called a plot. Let's call this the vision plot. We're going to leave everything there. Right now, it's going to plot count turtles, which is going to be flat because they reproduce and our rocks and our food don't change. So we can basically just use the same code before, which is mean vision of peeps. But this isn't going to work. Okay, it's red, it's throwing up an error. It's not going to work because when we opened this before, it needed to have the initial command plot mean vision of peeps. It's now nice and clean. And we can start to see a little bit of wiggle in that line. Not a great deal because the selection pressure is not great. And we can come to why that is in a second. Oh, it's starting to decline. We can see it's dipping just a little bit, 9.6, 9.5. It's getting a little lower. The reason, so first of all, we know there's change, but actually we're not seeing much selection pressure, which means we haven't really thought, there's something in the model that we haven't really thought about. Now, what the issue is that we're giving away free energy. So one of the other living peeps is allowed to reproduce, and they get to reproduce, and when they do that, they produce an offspring that might end up having more energy than they themselves have, right? So it just kind of becomes pretty stochastic. The agents in the model just want to wait around until they're randomly asked, and then it's fine. There's not really any selection pressure. Reproduction is not free. So let's imagine there's a reproductive cost to this. So we want to have the reproducer set energy. Let's just go energy. Let's have a really conservative little dip. We'll give them free energy, but we won't give them. But the cost of reproduction is -30. Now, when one of the weaker agents reproduces because they're randomly selected, they'll probably dip. Well, they'll get closer to 0, where they might have to check their own death. But it'll be on their next turn. So they set energy 30. They might actually dip below 0 here. But they'll still be able to pull this off because the check death function is not happening here. There's no interruption. So now, with a cost of reproduction being implemented, it seems likely to me that we're going to see some selection pressure to force vision to allow for the agents to reach more food. Okay, we're starting to get some wiggles. bit more variance than there was before. We're starting to see the emergence of kind of red and light blue phenotypes. Okay, now we're starting to see a bit more running away. Looks like there's only two phenotypes now, the red and the teal. Okay, we've dropped below 9.0 for the first time. Now we're starting to see some runaway selection. Very cool, right? So it is becoming more adaptive to have shorter vision because shorter vision allows you to get closer to the rocks. Now, the rocks themselves don't actually have any kind of energy cost associated with them. So what we'd inevitably see is that this vision variable is just going to drop all the way down to zero. There's no reason to not have zero vision, or rather to have very low vision. It's probably going to lock in at about 1.0, 1.5 would be my guess. If we turn view updates off, it can run a lot faster. We can see that this stops working, but this will continue to update. This will continue to update. Let's just let it run for a little while. Okay, so we're actually kind of reaching an equilibrium here, or it seems like we're reaching an equilibrium where this is the optimal kind of vision for the model, okay? Because if it's zero, you're just kind of randomly walking and you can never orient towards the food. So you still need at least some vision to outcompete some of your conspecifics, some of the other peeps in the model. So what we see here is vision is shortening so that they can get closer to the rocks. But that's kind of weird. Why would agents, this is not really biologically plausible. We're making strange assumptions here. We've kind of tied up this avoidance mechanism with a vision mechanism. So let's build on a new level. Let's build on some degree of cognition. Let's build a fear drive. And so what will allow our agents now to do is to look around their environment and then almost make a decision about how close they want to get to the rocks. Which means we can let our vision maybe get longer, greater, further, and allow their kind of fear drive to drop so they can get closer to the rock. So now we're getting two interacting variables. So pretty straightforwardly, we can do as we've done before. We need to give them fear. Let's give them a variable called fear. A variable for dictating how close each agent is willing to get to a rock. Okay, we've established that. Right now, it's doing nothing. We can look at our procedures, and if you remember, we have a nice little shortcut to find it. We have detect rocks. And so we have this. If any rocks in cone vision 90. So if they have identified any rocks in their visual cone, they simply turn around. But we don't want that. What we actually want is for them to turn around if they detect a rock, and if that rock is close enough that it triggers their concern. So rather than putting right 180 there just when they detect it, let's go if any rocks in cone fear 90. And we put the commands in. So we've got our fear here, but we haven't specified that value. So when we create our peeps, let's set fear to be the same as their initial vision. Why not? We want them to, if they detect it, they run away. But we're also going to want their fear to evolve. Set fear plus 1 of 0.1 and negative 0.1. Okay, so now we're going to let their fear evolve. In our vision plot, let's rename the vision plot to adaptation plot. Let's start changing these things. So the pen name for our vision is going to be vision. Let's add a new pen. Let's call this fear. Now we probably want to show the legend so these things become clear to us. Let's make vision blue. And let's make fear red. And we want to plot mean fear of peeps. So we should now start to see We see these two lines here. Right now they look like one line. Let's add another widget as well, just so we can see the actual number plot. It's going to be mean fear of peeps. Let's make that 3 and go mean fear. Okay, and we can see that these numbers are, let's just pause it right there, they're slightly different. They're not tied to each other. Although at the moment they seem to be, this is just kind of noise. For the first time we're starting to see separation in our plots. Very nice. We're seeing some blue and brown phenotypes emerging. We're seeing vision increase, but fear decrease. So there seems now to be an advantage in being able to see further, but being the kind of agent that's bold enough to walk closer to the rocks. So they're actually able to detect more in their environment than they're reacting to. So when we had fear and vision basically being the same thing, which was just vision, vision decreased until it found a nice stable point where they could get close enough to the rocks to eat. But now we've separated these two constructs. We've really thought about what our assumptions and what our variables represent, and we can start to see that there's a different set of relationships in the model. And this is one of the really important things when we think about emergence, when we think about building in these variables, is that we have to think about what these things actually represent and whether we've built too much into a single construct. Now, the other thing is about these very complicated models is that we have all of these other variables. If we just try to begin with, if we shifted initial vision down to 2, so essentially their fear and their vision is both very short, the question arises like, will their fear change and evolve? Will their vision evolve? Right now, we're just getting like a really strong random walk vibe that's just being, right now it doesn't seem to be better to have higher vision, which is kind of weird, right? Because we know that at a certain threshold, like when vision is high, eventually, let's make this go quickly, eventually vision will increase and fear will decrease. All right, there we are. We're starting to see it now. So we might want to start looking for a tipping point. What about when vision is set to 5? It's not 2, it's not 10, it's somewhere in the middle. We're not seeing any split. So this is actually kind of curious. This goes to show the unexpected interactions. What's happening is if we look at our agents and ask them to list who they are, ask peeps print who, all of these values were between 0 and 99. None of them have died yet. We can see this here. None of them have died yet. There's 98 getting right up there, but we have no triple digits. We have no 100s. They're all making too much energy. They're all finding too much food too quickly. So if we look here, the energy, 12,000 energy. They're all finding too much food. There's no selection pressure. There's no reproduction. So let's move the food value to something that's going to make life a little bit harder for them. There we are. We're starting to see some wiggle room. We're starting to see vision potentially increase, fear potentially decrease. It's still pretty noisy. We'll give it a bit more time. And we can start to very clearly see the selective pressure changing, and we've got our phenotypes in the model. Okay, we got these pink and blues. We even had a green in there. That's pretty cool. So when we make these models, when the more variables we have, they give us more control, but they give more interactions that become very difficult to interpret. But we can think about our variables. We need to really think about our assumptions. And when we're clear about what these things represent and what kind of behavior we're modeling, we can start to get interesting outcomes that might be expected or unexpected. So that's going to be the end of today's tutorial. Let's quickly summarize what we've covered. So what we did is we created a vision variable. We co-opted what used to be this vision variable. We made our global initial vision, and we passed vision itself onto the individual agents. We did so that so that when they reproduce, we could introduce a little bit of positive or negative variance. We thought clearly about what their behavior was representing. Did it make sense to become more short sighted? Surely there's some cognitive factor in there. So we created a fear factor or a confidence factor that allowed them to get closer even though they could detect things. And we built into this a very, very, very rudimentary reproduction system that had some unique benefits. Specifically, those benefits were every time an agent dies or is about to die, another living agent can reproduce, which has the benefit of keeping our population at a perfect 100 or at the set value we want it the whole time. We created we played around with align widgets, which is useful. Can't make too many mistakes there, but we used some monitors and we created some plots. Now there's a whole tutorial to be said about plotting. Right now we've used the kind of crudest and simplest approach to plotting by using the interface, but there's actually a lot of commands we could use within the code block to produce histograms or all other kinds of things, but we'll save that for another day. So for the moment, I'm going to annotate this code. I'm going to upload it to GitHub. You can click the link below, so like and subscribe. And you can also click the link below to access this code if you would like.